Hi, and welcome to another video on radiosondes. And in this video, we're going to talk about the sensors that are in the package that is borne aloft by the radiosonde. The atmospheric variables that are measured by the radiosonde are pressure, temperature, relative humidity, and wind. And there are sensors that measure each of those. We'll start out with pressure. Pressure has been measured a lot of different ways, a number of different ways by radiosondes. At first, it was measured by an aneroid barometer that had a pressure switch, meaning that as the sonde was borne aloft, the aneroid barometer or wafer would expand, and that was hooked to leverage that was connected to a barometric switch. So as the aneroid wafer or the aneroid diaphragm expanded, the switch would click on and off a circuit, allowing electricity to transmit not only the pressure, but also other variables down through telemetry. So in other words, the pressure sensor also acted as kind of a switch to provide information at various levels in the atmosphere. The problem with the aneroid was that it was not very accurate at higher temperatures. So sometimes there was a hypsometer that was employed by the radiosonde. It was a very small vial of fluid that would boil at known temperatures at very low temperatures. So as a result, they can figure out the temperature at which it boiled and therefore the pressure. So that was very accurate at low pressures. But for the most part, the aneroid worked pretty well at most pressure levels. Nowadays, the old aneroid has gone away, and instead of a mechanical unit, now we use, of course, more solid-state technology. And to do that, on the radiosonde motherboard is a temperature compensated silicon capsule, which is basically a pressure transducer. So it measures pressure as it goes up, and of course it has to measure very low pressures. Balloons typically are borne up to 50 or even 40 millibars. So it needs to measure anywhere from 1,000 to 20 millibars. The uncertainty in the pressure measurement is plus or minus 1 millibar. Temperature is measured either by a small rod thermistor or some sort of sensitive capacitor. Needs to measure temperature range of anywhere of plus 40 degrees Celsius all the way down to minus 60 degrees Celsius. So there is some uncertainty, typically about a half a degree of uncertainty, half a degree Celsius, that is. You can see the temperature sensor. It's the one that has TH with the arrow indicating that that is the sensor, and that's a thermistor right there. Relative humidity is measured using a sorption type device. The old radiosondes that used aneroid barometers often used a hygrostor, which was a carbon type sorption device. The relative humidity changed as a result of the resistance changed as a result of the relative humidity in the atmosphere. And if you know the temperature of the atmosphere, you can figure out the dew point. Nowadays, they use another type of device, also a sorption type device, but it's a capacitor type device. So the radiosonde needs to measure, of course, relative humidities from 0 to 100%. This has a rather high uncertainty of plus or minus 5%. Wind is measured based upon the movement of the balloon. Years ago, they would put a reflector on the radiosonde, and radar was used to track the balloon, and then from that figure out its position from time to time, and based on that, the wind. Nowadays, of course, with GPS, there is a little GPS receiver on board the radiosonde, and as the balloon moves, we know its GPS position from time to time with successive position reports. So based on the change in position over time, we can calculate the wind speed and wind direction. There are errors with radiosonde measurements. And some of the errors deal with response time, radiation, something called wet bulbing, its location, and then also the telemetry. With response time, you need to remember that the balloon is ascending approximately 5 meters per second. So that's about 15 feet every second. Now, if you have a sensor that responds, has a response time of only 10 seconds, a very long response time, then you'll see that the balloon has traveled a great distance before it sends, or before it sends a true report. Not a true report, but the report. So the report of the measurements at that altitude. So there are problems with response time. So the key here is that you need to have sensors that can respond very quickly. And with the advent of with electronic sensors, the response time has decreased dramatically. So with the old aneroids, there was a little bit of a lag, and also with the hygristor. Nowadays, things are a little bit better. For example, with temperature, the thermistors typically have a response time of about maybe a half a second or less, so that's very good. Humidity tends to be a little bit longer, might be a half a second, but it could be a little bit longer. I'm not sure of the new capacitor type device. We'll have to take a look at that when we look at all the sensors on the radiosonde in the next video. Radiation is also a problem, and it depends upon the size of the sensor. Typically, bigger sensors have more error with radiation. Smaller is better, therefore. Also depends upon how reflective the sensor is. And typically, radiosondes, of course, the package itself is white, but then they use reflectors to help reduce the amount of solar radiation that's impingent on the temperature sensor. And then finally, also remember that you need good ventilation going by the sensor. So the ascent speed of 5 meters per second is good enough to create good ventilation going around the sensor. So typically, radiation is not a big problem. Wet bulbing, however, is a big problem. And wet bulbing occurs when a sensor goes through, or when a radiosonde goes through a cloud and the sensor gets wet. In other words, the temperature sensor gets wet. So as it comes out of the cloud, it's coated with water, so it starts to evaporate. That evaporation cools the thermometer. It acts as a wet bulb. And as a result, the temperature drops dramatically, drops very rapidly, so much so that it's more than the dry adiabatic lapse rate. So it appears as if at the top of the cloud, the atmosphere is very unstable. That's not the case. It's just the sensor that got wet. You can usually tell by looking at the temperature and the dew point trace, and you can tell where there's cloud. And then as it comes out of cloud, you can see that the dew point decreases rapidly, and so does the temperature. So that is a problem that you need to be aware of and keep in mind when you're looking at radiosonde data. Another problem is location, meaning that the radiosonde travels a great distance downwind from its location. Remember that the radiosonde ascent typically takes an hour to 90 minutes or perhaps more. If there are very strong winds in the atmosphere, then that can travel a great distance downwind. So when you look at a weather map, you'll see the winds and the temperature and the dew point reported for a given location, right over that location. Remember, at higher altitudes like 500, 300, 250, and 200 millibars, that location is not necessarily right over the station. It may be 100 miles downwind from the station, so it may not be representative at higher altitudes of that given location. And then finally, as the balloon travels through the atmosphere, there may be some problems with signal loss. In other words, the sensor, the transmitter, may have degradation of signal as a result of atmospheric phenomena, or just because the sensor is a poor sensor. So you may have missing data as the balloon ascends through the atmosphere. So those are some of the errors associated with radiosondes.